Correction for this chapter. In mathematical formulae, instead of I, hear 1.
Recording by Linda Liu. Relativity, the Special and General Theory by Albert Einstein. Continuing Part 1, Sections 13 through 15. Section 13. Theorem of the addition of velocities, the experiment of Fizeau. Now in practice we can move clocks and measuring rods only with velocities that are small compared with the velocity of light. Hence we shall hardly be able to compare the results of the previous section directly with the reality. But on the other hand, these results must strike you as being very singular, and for that reason I shall now draw another conclusion from the theory, one which can easily be derived from the foregoing considerations, and which has been most elegantly confirmed by experiment. In Section 6 we derive the theorem of the addition of velocities in one direction in the form which also results from the hypotheses of classical mechanics. This theorem can also be deduced readily from the Galilei transformation, Section 11. In place of the man walking inside the carriage, we introduce a point moving relatively to the coordinate system K' in accordance with the equation x' equals Wt'. By means of the first and fourth equations of the Galilei transformation, we can express x' and t' in terms of x and t, and we then obtain x equals (v plus w) t. This equation expresses nothing else than the law of motion of the point with reference to the system K, of the man with reference to the embankment. We denote this velocity by the symbol W, and we then obtain, as in Section 6, W equals v plus w, equation A. But we can carry out this consideration just as well on the basis of the theory of relativity. In the equation x' equals Wt', we must then express x' and t' in terms of x and t, making use of the first and fourth equations of the Lorentz transformation. Instead of the equation A, we then obtain the equation W equals the sum v plus w over the sum I plus vw over c squared, equation B, which corresponds to the theorem of addition for velocities in one direction according to the theory of relativity. The question now arises as to which of these two theorems is the better in accord with experience. On this point we are enlightened by a most important experiment which the brilliant physicist Fizeau performed more than half a century ago, and which has been repeated since then by some of the best experimental physicists, so that there can be no doubt about its result. The experiment is concerned with the following question. Light travels in a motionless liquid with a particular velocity w. How quickly does it travel in the direction of the arrow in the tube T? See the accompanying diagram, Figure 3. When the liquid above mentioned is flowing through the tube with a velocity v. In accordance with the principle of relativity, we shall certainly have to take for granted that the propagation of light always takes place with the same velocity w with respect to the liquid, whether the latter is in motion with reference to other bodies or not. The velocity of light relative to the liquid and the velocity of the latter relative to the tube are thus known, and we require the velocity of light relative to the tube. It is clear that we have the problem of Section 6 again before us. The tube plays a part of the railway embankment, or of the coordinate system K. The liquid plays a part of the carriage, or of the coordinate system K', and finally the light plays a part of the man walking along the carriage, or of the moving point in the present section. If we denote the velocity of the light relative to the tube by W, then this is the given by the equation A or B. According as the Galilei transformation or the Lorentz transformation corresponds to the facts. Experiment decides in favor of equation B derived from the theory of relativity, and the agreement is, indeed, very exact. Footnote: Faisceau found capital W equals W plus V open parentheses I minus I over n squared close parentheses, where n equals C over W is the index of refraction of the liquid. On the other hand, owing to the smallness of VW over C squared as compared with I, we can replace B in the first place by capital W equals open parentheses W plus V close parentheses open parentheses I minus the fraction VW over C squared close parentheses, or to the same order of approximation by W plus V open parentheses I minus I over n squared close parentheses, which agrees with Faisceau's result. End footnote. According to recent and most excellent measurements by Zeeman, the influence of the velocity of flow v on the propagation of light is represented by formula B to within 1%. Nevertheless, we must now draw attention to the fact that a theory of this phenomenon was given by H. A. Lorentz long before the statement of the theory of relativity. This theory was of a purely electrodynamical nature and was obtained by the use of particular hypotheses as to the electromagnetic structure of matter. This circumstance, however, does not in the least diminish the conclusiveness of the experiment as a crucial test in favor of the theory of relativity, for the electrodynamics of Maxwell-Lorentz, on which the original theory was based, in no way opposes the theory of relativity. Rather has the latter been developed from electrodynamics as an astoundingly simple combination and generalization of the hypotheses, formally independent of each other, on which electrodynamics was built. End of section 13. Section 14. The heuristic value of the theory of relativity. Our train of thought in the foregoing pages can be epitomized in the following manner. Experience has led to the conviction that, on the one hand, the principle of relativity holds true, and that on the other hand, the velocity of transmission of light in vacuo has to be considered equal to a constant c. By uniting these two postulates, we obtain the law of transformation for the rectangular coordinates x, y, z, and the time t of the events which constitute the processes of nature. In this connection we did not obtain the Galilei transformation, but, differing from classical mechanics, the Lorentz transformation. The law of transmission of light, the acceptance of which is justified by our actual knowledge, played an important part in this process of thought. Once in possession of the Lorentz transformation, however, we can combine this with the principle of relativity and sum up the theory thus. Every general law of nature must be so constituted that it is transformed into a law of exactly the same form when, instead of the space-time variables x, y, z, t of the original coordinate system K, we introduce new space-time variables x prime, y prime, z prime, t prime of a coordinate system K prime. In this connection, the relation between the ordinary and the accented magnitudes is given by the Lorentz transformation, or in brief, general laws of nature are covariant with respect to Lorentz transformation. This is a definite mathematical condition that the theory of relativity demands of a natural law, and in virtue of this, the theory becomes a valuable heuristic aid in the search for general laws of nature. If a general law of nature were to be found which did not satisfy this condition, then at least one of the two fundamental assumptions of the theory would have been disproved. Let us now examine what general results the latter theory has hitherto evinced. End of section 14. Section 15. General results of the theory. It is clear from our previous considerations that the special theory of relativity has grown out of electrodynamics and optics. In these fields it has not appreciably altered the predictions of theory, but it has considerably simplified the theoretical structure, i.e. the derivation of laws, and, what is incomparably more important, it has considerably reduced the number of independent hypotheses forming the basis of theory. The special theory of relativity has rendered the Maxwell-Lorentz theory so plausible that the latter would have been generally accepted by physicists, even if experiment had decided less unequivocally in its favor. Classical mechanics required to be modified before it could come into line with the demands of the special theory of relativity. For the main part, however, this modification affects only the laws for rapid motions, in which the velocities of matter v are not very small as compared with the velocity of light. We have experience of such rapid motions only in the case of electrons and ions. For other motions, the variations from the laws of classical mechanics are too small to make themselves evident in practice. We shall not consider the motion of stars until we come to speak of the general theory of relativity. In accordance with the theory of relativity, the kinetic energy of a material point of mass m is no longer given by the well-known expression m v²/2, but by the expression mc² over the square root of the difference I minus the fraction v²/c². This expression approaches infinity as the velocity v approaches the velocity of light c. The velocity must therefore always remain less than c, however great may be the energies used to produce the acceleration. If we develop the expression for the kinetic energy in the form of a series, we obtain mc² plus m v²/2 plus 3a m v⁴/c² plus etc. When v²/c² is small compared with unity, the third of these terms is always small in comparison with the second, which last is alone considered in classical mechanics. The first term mc² does not contain the velocity and requires no consideration if we are only dealing with a question as to how the energy of a point mass depends on the velocity. We shall speak of its essential significance later. The most important result of a general character to which the special theory of relativity has led is concerned with the conception of mass. Before the advent of relativity, physics recognized two conservation laws of fundamental importance, namely the law of conservation of energy and the law of the conservation of mass. These two fundamental laws appeared to be quite independent of each other. By means of the theory of relativity, they have been united into one law. We shall now briefly consider how this unification came about and what meaning is to be attached to it. The principle of relativity requires that the law of the conservation of energy should hold not only with reference to a coordinate system k, but also with respect to every coordinate system k', which is in a state of uniform motion of translation relative to k, or, briefly, relative to every Galilean system of coordinates. In contrast to classical mechanics, the Lorentz transformation is the deciding factor in the transition from one such system to another. By means of comparatively simple considerations, we are led to draw the following conclusions from these premises. In conjunction with the fundamental equations of the electrodynamics of Maxwell, a body moving with a velocity v which absorbs Footnote 1. E sub 0 is the energy taken up, as judged from a coordinate system, moving with a body. End footnote. An amount of energy E sub 0 in the form of radiation without suffering an alteration in velocity in the process, has as a consequence its energy increased by an amount E sub 0 over the square root of the difference I minus v squared over c squared. In consideration of the expression given above for the kinetic energy of the body, the required energy of the body comes out to be the sum m plus E sub 0 over c squared times c squared over the square root of the difference I minus v squared over c squared. Thus the body has the same energy as a body of mass, m plus E sub 0 over c squared, moving with a velocity v. Hence we can say, if a body takes up an amount of energy E sub 0, then its inertial mass increases by an amount E sub 0 over c squared. The inertial mass of a body is not a constant, but varies according to the change in the energy of the body. The inertial mass of a system of bodies can even be regarded as a measure of its energy. The law of the conservation of the mass of a system becomes identical with the law of the conservation of energy, and is only valid provided that the system neither takes up nor sends out energy, writing the expression for the energy in the form the sum mc squared plus E sub 0 over the square root of the difference I minus v squared over c squared. We see that the term mc squared, which has hitherto attracted our attention, is nothing else than the energy possessed by the body. Footnote 2. As judged from a coordinate system moving with a body. End footnote. Before it absorbed the energy E sub 0. A direct comparison of this relation with experiment is not possible at the present time. Note: the equation E equals mc squared has been thoroughly proved time and again since this time. End note. Owing to the fact that the changes in energy E0 to which we can subject a system are not large enough to make themselves perceptible as a change in the inertial mass of the system, E0 over c squared is too small in comparison with the mass m, which was present before the alteration of the energy. It is owing to this circumstance that classical mechanics was able to establish successfully the conservation of mass as a law of independent validity. Let me add a final remark of a fundamental nature. The success of the Faraday-Maxwell interpretation of electromagnetic action at a distance resulted in physicists becoming convinced that there are no such things as instantaneous actions at a distance, not involving an intermediary medium, of the type of Newton's law of gravitation. According to the theory of relativity, action at a distance with the velocity of light always takes the place of instantaneous action at a distance, or of action at a distance with an infinite velocity of transmission. This is connected with the fact that the velocity c plays a fundamental role in this theory. In Part 2 we shall see in what way this result becomes modified in the general theory of relativity. End of section 15.